Hi, this is Dr. Karthik, and in our today's lecture series, we are going to discuss about the controllers. A controller is a device introduced in the system to modify the error signal and to produce a control signal. So what does the controller does is it modifies the transient response of the system. Now you can see we have included a controller in the actual system where this controller, the error signal produced by the error detector is always a weak signal. So therefore this signal needs to be amplified and then converted into a control signal in order to control the plant parameters. Now for that we are going to use this controller. So the main purpose of the controller is to modify the error signal and to produce a control signal. And this action you call it as the control action. So there are various types of controllers available in control system, and in today's lecture we are going to discuss about the proportional controller, the integral controller, the derivative controller, and a combination of all these three controllers. To start with, now the first one is the proportional controller. So the proportional controller, as seen over here, now it produces an output which is proportional to the input signal. Now I can see here our E of t is the error signal, and you have a controller. So E of t, it occurs as an input to the controller, and U of t, yes, that's nothing but the output. So what does this controller does is it produces a signal which is proportional to the error signal. So when you equate this proportionality, now we get a constant which is Kp. Now you call it as the proportional gain. Now after applying Laplace transform to the above equation, now you can see U of s by E of s is equal to Kp. So what does actually this reveals is that now this proportional controller, it amplifies the error signal by an amount of Kp. So the error signal, now it has been amplified. Now that's the main purpose of our controller. It amplifies by Kp. Now, and actually what it does is it increases, so the loop gain is also increased. So since the loop gain is increased, now this controller, it easily tracks or it increases the steady state tracking accuracy of the system and thereby improving the relative stability of the system. Now that's the main advantage of our proportional controller. Now the second controller is the derivative controller. Now this derivative controller, what it does is it actually produces an output. So you can see U of s, that's nothing but the output. It produces an output which is a derivative of the input signal. So actually this acts on the derivative of the input signal. And mostly the derivative controller is not going to be used individually, rather than it is going to be used in combination with other controllers. So now we can see after amplification, now we got this Kd of s. Now this is nothing but our output from the derivative controller. So this controller, mainly it is effective only during the transient period, and it also, since it does not act on the error signal, it acts on the rate of change of the error signal. Now there is always a possibility that it amplifies the noise signals also. So the derivative controller, it is used to make the unstable control system into a stable one. So which means this derivative controller, rather than acting on the error signal, it anticipates the error. It anticipates the error and it produces a corrective measure earlier to before the error signal occurs. So that is why it makes the unstable control system into a stable control system. This is our derivative controller. The next is the integral controller. So you can see the integral controller, it produces an output which is the integral of the error signal. It produces an output which is the integral of the error signal. So you can see U of s by U of s is equal to Ki, we call it as the integral gain, and then since we are taking Laplace transform of integral, we give it as 1 by s. Now the main purpose of the integral controller, what it does is it decreases the steady state error. Your proportional controller, it introduces an error, whereas the integral controller, it decreases the steady state error. Now since this produces the introduction of this integral controller, it produces an oscillatory response. Now there is always a chance this controller may lead the system to an unstable system. Now that's the main drawback of this integral controller. So therefore, instead of individually using this proportional, integral and derivative controller, we are going to combine these controllers so that to take the advantages of individual controller. So one such controller we'll discuss is, the first one is the proportional derivative, which means the output signal, now as seen over here, it is proportional to the derivative of the derivative of the error signal as well as proportional to the error signal. So it is a sum of the proportional and the derivative controller. Okay, so you can see Kp and Kd. Kp is the proportional controller and Kd is the derivative gain. Now this controller, as I already told you, the derivative controller, it anticipates the error, thereby improving the stability of the system, whereas the proportional controller, it tracks that is the tracking accuracy is very high for a proportional controller. So both the advantages are made use in the proportional controller. Then comes the proportional integral controller. Again, the output over here, it is equal to the sum of the that is the signal proportional to the error signal, and it is proportional to the integral of the error signal. So Kp is the proportional gain, K is the integral gain. So here the proportional integral controller is used to decrease the steady state error without affecting the stability of the system. So the stability of the system is not affected. So this is proportional integral controller. Now in order to make use of all three controllers, the advantages of all three controller, now we are going to use the PID controller, which is proportional, integral and derivative controller, where you can see it is the sum of the output, it is the sum of the error signal proportional to the error signal, it is proportional to the integral of the error signal, and it is proportional to the derivative of the error signal. So here it is used to improve the stability of the system and also to decrease the steady state error. So all three advantages are realized in this proportional integral controller. So these controllers, they can be realized using the op-amp circuits, which is the practical application of the PID controllers, and the Kp, Ki and Kd, that is the proportional gain, integral gain and the derivative gain, they can always be tuned using special technique, which we will be discussing later in this lecture series. So thank you for your patient listening. Thank you very much.